In this presentation, we'll discuss information that is specific to Alabama. Our state representative is Braun Bradley of Bradley Environmental, and he can be reached at the number and email address shown on the screen. Check with our state representative or visit our website for product suppliers in your area. During this training video, we'll cover many of the requirements to successfully design and install advanced Enviroseptic systems. However, to have a complete understanding of the product, you must read the entire Presby manual for Alabama. Now let's discuss some of your state-specific requirements. The design manual uses 150 gallons per day as the daily design flow for each bedroom. The minimum daily design flow for any system is 300 gallons per day. The advanced Enviroseptic pipe required for a residential system is calculated at a minimum of 70 feet per bedroom. For example, a two-bedroom system would require 140 feet of AES pipe to adequately treat the daily flow. If the system being designed is for a commercial application, the AES pipe requirement is calculated at 1 foot for every 2 gallons of daily flow. Consult the factory for recommendations if the effluent strength is high. All separation distances are measured to the outermost edge of the system sand. Vertical separation distances are measured from 12 inches below the advanced Enviroseptic pipe, which is the bottom of the system sand. A minimum of 24 inches must separate the bottom of the advanced Enviroseptic pipe from the seasonal high water table or restrictive feature, which is described as a layer with a perk rate greater than 240 minutes per inch. Continuing with our state-specific information, Table A of the manual is used to determine the minimum system sand bed area and the bed's length to width ratio. It is important to note that the table already takes into account all state-approved reductions in dispersal area as compared to pipe and stone. No further reductions are needed. Table B controls the allowable system slope, site or terrain slope, and the allowed bed configurations for a soil's perk rate. All systems, regardless of design flow, are required to be vented. You'll remember from an earlier presentation, this is done to ensure the field will remain aerobic, or supplied with air. If any portion of the bed extends above the original grade, the fill covering the field must have side slope tapers of 2:1, with 3:1 being required on the downslope side of a sloping bed. All advanced Enviroseptic rows must be laid level within 1 inch from the start of the row to the end of that same row, regardless of its length. A replacement area, also called a reserve area, used in the unlikely event the original fill fails, is required for advanced Enviroseptic systems. However, the designated reserve area is the same location as the original Presby field, understanding that all unsuitable material must be removed prior to field replacement. It's worth mentioning again that the Presby pipe is supplied in 10-foot lengths. These are often referred to as unit lengths or just units for short. The pipe can be cut to any desired length. Now let's move on to some illustrations of bed layouts approved for use in Alabama, all of which have been introduced in earlier presentations. Illustrated here is a basic serial bed layout, which is permitted in Alabama, but is limited to no more than 600 gallons per day of daily flow. A bed is different than a trench in that it will have more than one row of Presby pipe, has a minimum row spacing of 18 inches center to center, and is allowed to be constructed either level or sloping. You'll remember we discussed how the system slope can vary from the terrain slope. Presby beds do not have to be constructed parallel to the existing grade, although this is the most common practice. When the bed slopes over 5%, we ask that you group all rows to the high end of the field and place the system sand extension entirely on the downslope side. This system sand extension only needs to be 6 inches thick and extends a minimum of 3 feet beyond the edge of the Presby pipe. In this illustration and in the manual, this is shown as 2.5 feet minimum when measuring from the tall portion of the system sand. So don't be confused. They both are providing the same system sand extension. The only difference is where we are measuring to. Depending on the system sand bed area required by Table A, the system sand extension may actually be longer than 2.5 feet to provide enough dispersal area to meet the minimum area requirement. A vent must be attached to the end of the last row in the series. This ensures air is drawn through every foot of Presby pipe. It's important to note that the row spacing is a minimum. The designer is free to increase this spacing if they desire. When the daily flow exceeds 600 gallons per day, a combination of more than one serial section must be used to divide effluent to different portions of the field. We call these beds combination systems, which simply means there are a combination of more than one serial section in the bed. Like basic serial systems, a vent must be connected to the end of each serial section. In this bed, there are 2 serial sections with the ends connected to a vent manifold, which is then taken to a single vent stack. The serial sections, however, could have been vented separately. Depending on the daily design flow, a combination system may have more than 2 serial sections. Combination systems are allowed to slope in the same way as basic serial systems. The familiar D-box layout is also allowed. The field may be constructed level or sloping. If the field slopes, the D-box must be placed at the highest elevation. The system sand extension should also be placed entirely on the downslope side of the bed. Venting for this layout requires the vent manifold to be connected to the far ends of all the rows before being taken to the vent stack. This configuration also requires all the rows to be of equal length. And finally, flow equalizers are required on all used outlets of the D-box delivering effluent to the pipes, which helps maintain a balanced distribution to all the rows in the event the D-box goes out of level. Multiple bed layouts are commonly used when there is a site restriction or the length to width ratio prohibits a single wider bed. The D-box is placed between the fields. Once again, flow equalizers are required on the D-box outlets. Each bed of a multi-bed layout must have at least 50% of the required Presby pipe. More is allowed, but never less. In this example, each serial section is vented separately. However, they could have been joined together and taken to a single vent stack. Let's quickly review serial sections for a moment. If the daily design flow is 600 gallons per day or less, a single serial section can be used. We call these basic serial systems. When the daily design flow exceeds 600 gallons per day, the flow must be divided to more than one area of the field. The amount of pipe in each of these sections is determined by dividing the total amount of pipe required by the number of sections being used. Let's do an example. If we have a 3-bedroom system using 150 gallons per day per bedroom, our total daily design flow is 450 gallons. Because this does not exceed 600 gallons per day, we only need one serial section. But let's use the formula anyway to check our answer. The formula says, to find the number of serial sections needed, divide the daily design flow by 600 and then round up to the nearest whole number. So, taking 450 gallons per day divided by 600 gallons per day per section gives us 0.75. Rounding this up to the nearest whole number gives us 1, which agrees with our earlier answer. Let's do another example. If the daily flow is increased to 6 bedrooms, this time using a total of 900 gallons per day, how many serial sections do we need? Following the rule, we take 900 gallons per day and divide it by 600 gallons per day per section, resulting in 1.5. Rounding this number up to the nearest whole number gives us 2 serial sections required. Another way to think of this is that the D box must use at least 2 outlets to divide flow to the field. If this 6-bedroom system had required the use of 300 feet of Presby pipe, each serial section must have at least 150 feet. And some final notes. You are always free to use more serial sections or pipe than are required. You should also remember the traditional D-box layout, which feeds each row individually, is not subject to this rule. Don't assume you can feed 600 gallons per day to each individual row. The serial section rule only applies to beds using serial distribution. Now let's introduce the actual tables used to size a system. Table A in the Alabama Manual is used to find the maximum loading rate given in gallons per day per square foot for a given perk rate. It also provides the minimum length to width ratio. Highlighted is an example of how to use the table. Find your soil's perk rate in the far left column. Move to the right to find the maximum soil loading rate given in gallons per day per square foot. This value, divided into the daily design flow, is used to determine the minimum system sand bed area, also known as the dispersal or basal area. Continuing to the far right column, you'll find the minimum length to width ratio of the system sand bed. Highlighted is the perk rate range of 6 to 10 minutes per inch. Moving to the right, we see that the maximum soil loading rate, which is also known in the industry as the application rate, is 1.67 gallons per day per square foot. And in the far right column, we see that the minimum length to width ratio is 2 to 1. That simply means the system sand bed length divided by the system sand bed width must be at least 2. Table B is used to control the allowable system slope, site slope, and finally the bed configurations that can be used on soils of a given perk rate range. As an example, highlighted is the soil perk rate range of 15 minutes per inch and less. Table B is limiting the maximum system slope to 25%. The maximum terrain slope our field can be constructed on to 33%. We also note that all bed layouts, like basic serial, combination, and multi-bed configurations, are allowed for this perk rate range. And a final note, just because Table B allows a system slope greater than 0, doesn't mean the designer can't choose to use less slope or none at all. Now that you've been introduced to the sizing tables, let's talk about the process of designing an actual system. Shown here are 5 tasks or steps used in the design process. The first task is to find the soil's loading rate and length to width ratio from Table A using the soil's perk rate. Now calculate the minimum system sand bed area using the application rate just determined. Task 2 takes us to Table B, where we'll find the maximum system slope, maximum site slope, and allowable bed configurations. Task 3 asks that we calculate the minimum amount of advanced enviroseptic pipe required to adequately treat our daily design flow. Task 4 requires the selection of the AES row length after calculating the minimum row length needed to satisfy the length to width ratio. We can then determine how many AES rows will be needed. Finally, in Task 5, we calculate the system sand bed width. The system sand bed width must always be wide enough to cover all the rows used in our design, which may provide more sand bed area than is required by Table A. The sand bed's length to width ratio is then verified. Let's work through a design example for a daily design flow for bedrooms, which is 600 gallons per day. The soil has a perk rate of 12 minutes per inch. The site or terrain slopes 10%, but we want to construct our field level because the owner wants a flat backyard. Task 1 takes us to Table A, and we use the soil's 12-minute per inch perk rate to find the soil's loading rate of 1.52 gallons per day per square foot. Dividing our daily flow of 600 gallons by 1.52 requires a minimum of 395 square feet of system sand bed area, which is also known as the dispersal or basal area. We also note the minimum length to width ratio is 2:1. That means the sand bed must be at least twice as long as it is wide. In Task 2, we determine if the field we want to construct will fall within the limits imposed by Table B. For our 12-minute per inch perk rate, a system is allowed to slope up to 25% and be constructed on terrain with up to 33% slopes. Our field is going to be constructed level and be placed on a site that has only a 10% slope. We fall well within the limits of Table B. We also note that we can use any bed configuration shown in the manual. In Task 3, we calculate the total amount of Presby pipe that will be required for our daily flow of 4 bedrooms. The manual requires a minimum of 70 feet of advanced enviroseptic pipe for every bedroom in our design. So at least 280 feet of Presby pipe must be used in this example. Task 4 asks that we select a row length and then calculate the number of rows needed. In most cases, the length to width ratio will never be an issue. However, if you use the formula shown on the screen, you can almost always be sure to satisfy this requirement the first time through the process. The formula says to multiply the minimum system sand bed area calculated in Task 1 by the length to width ratio and take the square root. This will actually provide the minimum system sand bed length. However, the advanced enviroseptic row length will be 1 foot shorter than this number, and is why we then subtract 1 foot to get our final answer. In our example, we multiply 395 square feet times 2 because the length to width ratio is 2:1, and then take the square root of that product. Finally, we subtract 1 foot to find the minimum advanced enviroseptic row length of 27.1 feet. But we always prefer longer rows to shorter ones, so we're going to use a 40-foot row length because we have no site constraints. Using this 40-foot row length means we'll need 7 rows to use all 280 feet of the required Presby pipe. In Task 5, we calculate the system sand bed width using the number of rows determined in Task 4, and then verify that we have satisfied both the length to width ratio and the minimum system sand bed area required by Table A. In the last step, we calculated that we needed 7 rows. To cover all these rows with sand, we'll require the sand bed width to be 11 feet. Now let's check to make sure we have enough sand bed area. The sand bed length will be the advanced Enviroseptic row length plus 1 foot, or 41 feet in this example. We multiply that times our sand bed width of 11 feet and find we have 451 square feet of sand bed area in this design, which is greater than the 395 square feet required. If it hadn't been, we would increase the sand bed width or length until we had at least the required sand bed area. Next, we need to check our length to width ratio. Dividing our sand bed length of 41 feet by our sand bed width of 11 feet results in a ratio of 3.7 to 1, which far exceeds our 2 to 1 requirement. Now let's look at an illustration of this system. Because our daily design flow was less than 600 gallons per day, I've chosen to use a basic serial layout. With basic serial systems, you are not required to use a D-box, so this system can connect directly to the septic tank outlet. And finally, a vent is attached to the end of the last row in the series. Note that 12 inches of system sand is always placed below the advanced Enviroseptic pipes. Let's work through another example. This time, we'll use a daily design flow of 5 bedrooms, which is equal to 750 gallons per day. We have soils with a perk rate of 60 minutes per inch, and this site has a terrain slope of 15%, so we'll match that with a 15% system slope if Table B allows. Because our daily design flow exceeds 600 gallons per day, we will need at least 2 serial sections. Now that we have a design criteria, let's work through the process. Task 1 takes us to Table A, and we use our soil's perk rate to find the soil loading rate of 0.5 gallons per day per square foot, requiring a dispersal area of 1,500 square feet. And finally, Table A is requiring a length to width ratio of 6 to 1. In Task 2, we find that Table B allows a system to slope up to 15%, which is our preference in this example, and the site or terrain to slope up to 20%. All standard bed configurations are allowed, and we're going to use a standard combination layout. Task 3 asks that we calculate the amount of advanced Enviroseptic pipe required for our daily flow. We know that 70 feet of advanced Enviroseptic pipe are required per bedroom, so we'll need 350 feet of AES for our 5-bedroom loading. In Task 4, we select a row length and then calculate the number of rows needed. The formula says to multiply the minimum system sand bed area, calculated in Task 1, by the length to width ratio, and then take the square root of this product. We then subtract 1 foot to find our minimum advanced Enviroseptic row length. In our example, we multiply 1,500 square feet times 6, because the length to width ratio is 6 to 1, and then take the square root, then subtracting 1 foot to find the minimum AES row length of 93.9 feet. But we'll round that up to 95 feet for ease of construction. Using 4 rows 95 feet long, we'll use 380 feet of Presby pipe, which exceeds the 350-foot minimum required for our daily flow. The minimum sand bed width needed to cover all the advanced Enviroseptic rows in this example is 6.5 feet. But this will not provide enough sand bed area to satisfy Table A. Dividing 1,500 square feet by our 96-foot sand bed length results in a minimum sand bed width of 15.63 feet. We'll round this up to 16 feet for ease of construction. Next, we need to make sure our length to width ratio is acceptable. Taking the 96-foot long sand bed divided by the 16-foot sand bed width gives us an exact length to width ratio of 6:1, which satisfies the minimum requirement from Table A. If it hadn't, we would have had to go back and select a longer row length and recalculated the sand bed width. Let's have a look at an illustration of this design. Unlike the previous example of a level field, this bed has been designed to match the existing terrain slope of 15%. As a result, a system sand extension is required and is placed entirely on the downslope side of the Presby field. The field is shown with 2 serial sections, which is the minimum for 750 gallons per day. The ends of each serial section have been connected with a vent manifold so they can use a single vent stack. And finally, all used D-box outlets must have flow equalizers. This is a section view of the same field. Let's assume the seasonal high water table forced a portion of the bed above the original grade. The fill covering the bed must have side slope tapers of 2:1 on all sides, except a 3:1 is required on the downslope side. In practice, the 3:1 will likely be 4:1 or more due to the system sand extension. Remember that at least 12 inches of cover is required over the very end of this extension. That brings us to the end of the state-specific presentation. Not all the options or configurations described in the Presby manual have been discussed. Please take the time to read the manual before attempting a design or installation. Let's review some of the key topics just discussed. Each bedroom is calculated at 150 gallons per day. And the minimum daily design flow for any system is 300 gallons per day. The Presby pipe required for a residential system is calculated at a minimum of 70 feet per bedroom. For a commercial application, the advanced Enviroseptic pipe requirement is calculated at 1 foot for every 2 gallons of daily flow. But remember, always consult the factory for high-strength effluent recommendations. All separation distances are measured to the outermost edge of the system sand. Vertical separation distances are measured from 12 inches below the advanced Enviroseptic pipe, which is also the bottom of the system sand bed. A minimum of 24 inches must separate the bottom of the advanced Enviroseptic pipe from the seasonal high water table or restrictive feature. A restrictive feature is described as a layer with a perk rate greater than 240 minutes per inch. Continuing with our state-specific review. Table A of the manual is used to determine the minimum system sand bed area by providing the soil's maximum loading rate in gallons per day per square foot. This table already takes into account all state-approved reductions in dispersal area as compared to pipe and stone. No further reductions are necessary. Table B controls the allowable system slope, site or terrain slope, and the allowed bed configurations for a soil's given perk rate. All systems, regardless of daily design flow, are required to be vented to maintain an aerobic environment. If any portion of the bed extends above the original grade, the fill covering the field must have side slope tapers of 2:1 or 3:1 on the downslope side of a sloping bed. All advanced Enviroseptic rows must be laid level within 1 inch from the start of the row to the end of that same row, regardless of the row's length. A replacement area, also called a reserve area, used in the unlikely event the original fill fails, is required for advanced Enviroseptic systems. However, the designated reserve area is the same location as the original Presby field, understanding that all unsuitable material must be removed prior to field replacement. In the next presentation, you'll be introduced to the construction techniques used when installing a Presby field. Thanks for watching.